I will, I will, fortunately, so I will make sure I go over. So as by 3:05. Okay, you can leave at 3:05. You guys are so cagey today. I don't know what you're like, all whispering and some kind of conspiracy. I don't know what's going on.
He's so excited.
Well, but I heard it's not a political meeting. It's because you what's that?
Right, but then you warned us that didn't mean it was political.
It's just a chat. Nothing.
It's a silent. Okay, well, I don't think I need to edit this yet, but we're working on it. So I'm gonna begin with a word of prayer. So I don't like editing. Dear Father, we thank you for this day. I thank you for the students. Just ask you just bless our work today, Lord. In your name I pray. Amen. Let me begin with a question. Is what is the degree of the sixth root of 2 over q adjoin the square root of 2? Give me an answer. You guessed 3. So your claim is that x cubed minus the square root of 2, which is in, of course, q adjoin square root of 2 of x, is irreducible. And the minimal polynomial of the sixth root of 2 with respect to q adjoin square root of 2, whoa, what a mouthful, of x is in fact that same one, right? Right?
Yeah.
How would you prove that that's irreducible? In other words, what would it mean to show that, I mean, it's a cubic, right? So we have, quadratic and cubic are most nice, right? Because it's irreducible if what? It doesn't have a 0, right? So is it clear, I mean, if I just let f of x equal to x cubed minus the square root of 2, then I suppose we could look at things of the form, a plus b root 2, right? And so the question is, if I do that, right? Oh, look at that. I cube that thing and then subtract the square root of 2 and set that equal to 0. We need to show there does not exist AB in Q solving the above, right? If I was to take a direct approach, I mean, that's one thing I would try to calculate, right? Because that, I mean, if it does have a 0, if that does have a 0 in Q adjoin root 2, that means that I could plug in something of the form rational linear combination of 1 and root 2, and I'd get back 0, right? So if it's irreducible, that means that there is no solution to that equation. Thankfully, this is not how we have to do it, okay? So we can get around this by making the following picture, all right? So we have Q adjoin the sixth root of 2. That's over Q adjoin root 2, and that's over the base field of q. By the example, I still haven't worked out, and I probably should, but who knows if I'll ever get around to it. We know that anytime you adjoin a square root, it's a degree 2 extension, right? Because we're not over field of characteristic 2, so no monkey business here. So that's a degree 2, right? And we also know, going from the top, from the bottom to the top, right? Going from here to here, that's degree 6. Why? Because x to the 6th minus the, 6th root of 2 is what? Oh, excuse me, x to the 6th minus 2, rather. I'll get with it eventually here. This guy. That's the, this is the minimal polynomial of the 6th root of 2, right? Over the rationals, yeah? And that's irreducible because Eisenstein p equals 2, right? So we know that, what do we know? We know that q adjoin the 6th root of 2. Oh, good grief, my notation. Q adjoin the 6th root of 2 over q is, by the way, equal to what? Q adjoin the 6th root of 2 over q adjoin root 2 times q adjoin root 2 over q by the, right? Extend the extension theorem, right? Whatever you want to call that. We proved this 2 classes ago now at the end. And so let's put in, what do we know here? This is 2. This is 6. Therefore, q adjoin the 6th root of 2 over q adjoin square root of 2 is degree what? It's 3. Now, what does that have to do with Bethany's original claim that has degree 3? This all goes together. X cubed minus root 2 has the 6th root of 2 as a 0. That means that the degree of the q adjoin root 6 over q adjoin root 2 is at most 3. Right? It's at most 3, but the fact that this is equal to 3 means that, in fact, it's equal to 3, and that means that the polynomial here, x cubed minus 2, is in fact irreducible. Because remember we had this theorem that the extension reaches its maximal degree if and only if the polynomial is irreducible. I forget what the number on that theorem was, but we proved it last time, right? See, this is why we shouldn't take breaks. If we could just have one continuous 40-hour lecture. and then I'd be done. Yeah, I'd be done. I'd be dead. Let's see here. Was it Prop 12?
The one with 3 parts?
Prop 12. It's definitely related to Prop 12.
What were you saying with that first theory?
Because if we look at this polynomial and we plug in the 6th root of 2, we get 0. Which means that the degree of q adjoin 6th root of 2 over q adjoin root 2 is at most 3. There's a possibility, ignoring the fact that we know it's 3, that this could somehow factor.
Because that's a polynomial in q adjoin root 2.
Right.
Okay.
But that doesn't happen, right? Because by the degree multiplication formula, we get that it's 3, which then circuitously proves this is irreducible, which is ever so lovely because it saves us from the drudgery of trying to think through whether or not you can solve these equations. right? So, this is a very nice workaround. Okay. Okay, so moving along here, attempting to move along. Definition. K over F is finitely generated if there exist elements alpha 1, alpha 2, alpha k in K, big K, such that K is F adjoined alpha 1, alpha 2, alpha k. This is the definition. And from that, he gives us the following lemma. F adjoin alpha beta. We can think of this, in fact, as F adjoin alpha, then adjoin beta. All right. So F adjoin alpha comma beta, it's the smallest field, right, which contains F as well as alpha and beta. And the proof of lemma 16 just basically sorts through that, the fact that what's on the right-hand side versus what's on the left-hand side is the same. Both of these are just a set which contains, of course, the field F, but also the elements alpha and beta. So this is just like, we've seen this sort of thing before. Just a reminder, we can look at, for example, bivariate polynomials, right? You could look at those as what? We had this kind of, it's kind of the same thought, right? I mean, like you can extend adjoin X and then you adjoin Y, and so it's really the same kind of thing. And this extends, likewise, if we are extending by more things, if we have K equal to F adjoin alpha 1, alpha 2, alpha K, then we can look at that as F adjoin alpha 1, all the way to alpha K minus 1, right? That's a field. You take that field and you adjoin alpha K to it, right? So like if you can do it twice, you can do it 3 times, 4 times, you can do it K times, all right? And then, so let's see here. So if you look at this, the degree of K over the field with alpha 1, alpha to the K minus 1, right? Let's see here. I'm not saying this right yet. I want to say K over F. The degree of K over the base field would be equal to the degree of K over the almost all the way extended 1, right? See what I'm doing? Maybe I should do it for 3 rather than K, but I'm just going to be greedy. All right? And then what? You can, again, right? So this would be, let's see, where should I break it? I don't, this one? What's that? At 7. At 7. You've been talking to Joe. Let's see here. Joe is a student I had in advanced calculus last time, or the time before. I think it was last time, who wanted to use 7 as a variable.
Oh, I thought you mentioned this.
Yeah. It's one of the more offensive ongoing jokes a student has tried to do in my classes. But oh, shnikes. I can't think. Oh, this is horrible. Let me stop this. This is horrible. It's horrible. This is just not the right notation. I mean, what I wrote was not, I don't think, wrong. I don't think it was wrong. It's just the wrong way to write it, okay? So he says this. You have f, which we could think of as f sub 0, and that's a subset of f1, which is a subset of f2, which is a subset of f3, which is a subfield of da-da-da-da. Finally, you get to the kth one, which we're saying is equal to k. So here, like f sub j is equal to f with, this notation is what I was needing, alpha 1 all the way out to alpha j adjoined. All right? And then like the question is, what's the formula, what's the degree of k over f here? You can look at it as, well, it's the degree of k over the k minus 1th intermediate, and then the k minus 1th over the k minus 2th intermediate, and so forth and so on. Finally, we get to like the second over the first intermediate, and then finally the first intermediate field over the base field, f0. Let me draw a picture here. So what I'm trying to discuss at the moment is how the degrees are like something like the cumulative, multiplicativity of the extension 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 of the extension. All right, anyway. K minus 1, K minus 2, dot, 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 2, 1, F, all right? So suppose that, I mean, let me just write the degrees over here, right? So, oh, I think this is yours.
That is mine. Looking for that.
There you go. You're welcome. So, N1, N2, N K minus 2, Nk minus 1, and finally Nk. In other words, I'm saying this, what happened? Camera beeped? Why did it beep? Well, it looks like it's recording. Why did it beep then? This is most mysterious. Okay, so this is K, right? And this is F in the language at the moment. Anyway, the point is this degree is Nk, Nk minus 1, N2, N1. So if you do like a degree 2 extension followed by a degree 3 extension, you get a degree 6 extension, right? If you do a 2, then a 3, then a 5, you get a, whatever that is, degree 30 extension, so forth. And he also describes in here around page 525, like what the basis looks like and how these come together. Let me try to get to something here. All right. Let's see here. He says, if we consider Q adjoin the square root of 2, the square root of 3, right? then of course we can look at that as what? Q adjoin the square root of 2 adjoin the square root of 3. So the question is, what's the degree of this extension? I mean, look, what I'm asking is, what is, what's the degree of the total extension here? Right. This is the overarching question that I'm asking: is what's the degree of Q adjoin root 2 and root 3? All right. Okay, so some things. I mean, see, so let's see here. Let me try to break it down here. So it really boils down to knowing I mean, pick your poison here. So this we know is 2. Yeah.
The first one's over 2, right?
On the left.
Very left of the equation.
Thing that you wrote in purple.
Oh, yeah. Sorry. Thank you. I didn't even see it. I'm looking right at it. So we know that's 2, right? And what else do we know? Check this out. We know f of x equals x squared minus 2 times x squared minus 3 has what? Square root of 2 and square root of 3 as zeros. Therefore, what's the maximum possible degree of Q adjoin root 2 root 3? It can be no more than 4, because that takes root 2 and root 3 as zeros. If irrationals, root 2 and root 3, that makes this field. Okay, so the question then is it 4, right? Is it 4? And so how do we, this time we had no workaround. Like last time, what I just erased, we had that degree 6 going from the top, right? But I don't have a nice argument that this is irreducible. It's quartic. Do you remember the proving the quartic was irreducible homework problem in abstract 1? Yeah, we don't want to do that. So is this degree 2? What does that amount to? In other words, is x squared minus 3, right? So I should look at this as this, right? See what I did there? Should I, is this irreducible in the polynomials with coefficients taken from q join root 2 over x? Is that irreducible? Over q adjoin root 2. So what do? We actually flesh out the calculation I didn't want to do in my first example today. We plug in an arbitrary q adjoin root 2 element and show that it can't be a 0. And if there's no 0 to this quadratic, that means it's irreducible, right? So we look at, a plus b times the square root of 2 squared minus 3 equal to 0, right? And we hopefully can easily show that there is no rational solution to this. So you multiply that out, what you got? You got yourself an a squared plus 2ab root 2 plus 2b equals to 3.
2b squared, right?
2b squared, yes. So I can see two things from that immediately, using the fact that, Q adjoin root 2 is a vector space with basis 1 and root 2. So I can equate the coefficients of, like the root 2 coefficients gives me that 2ab is equal to 0. And on the flip side, the coefficients of 1 here gives me a squared plus 2b squared equals to 3. So, you know, either a is 0 or b is 0, right? If a is 0, what happens? A equals 0 gives us that 2b squared equals to 3, right? Which says that b squared is 3 over 2. Which would say that a rational number has a square which is 3/2. Can you do that? I mean, more just sort of directly, and number theorists don't like this kind of thing, but if you'll allow me a second here, take the square root of both sides. This is not in Q, right? Why don't we ever argue like this? We just don't. You know? We're always afraid to do things outside of where we're working, right? It's like, that's irrational. So why? You're working rationals. Why? Anyway, I shut up. So a equal to 0 didn't work because it made b irrational, right? And how about b equals to 0? B equals to 0 gives us what? It gives us a squared equals to 3, which implies that a is equal to, like, you know, plus or minus square root of 3. Again, far from rational. So, in short, this polynomial is irreducible. Therefore, Q adjoin root 2 and root 3 is a degree 4 extension over the rationals. Right? So therefore, x squared minus 3 is irreducible over Q adjoin square root of 2. Does that make sense? I hope it makes sense. Now, so as he goes on here, we get the corollary, corollary 18. Make sure I didn't miss one here. Wait a minute. Oh yeah, I missed one. I'm sorry, I missed one. Theorem 17, I should probably write down. Theorem 17, it says that the extension k over f is finite, all right, if and only if what? K is generated by a finite number of algebraic elements over f. How does this differ from what we talked about the other day? What was the theorem we proved? We proved that an extension is finite if and only if it's what? Algebraic, right? But what was the definition of algebraic? It meant that any element of the extension was algebraic, right? What's this saying? This is saying something a little bit more nuanced. It's saying that if you have a finite extension, then not only is every element algebraic, but in fact you can generate any element from a finite collection of them. See, it's saying that k over f is finite means that k is actually equal to f adjoin these generators. We didn't have that last class. We just had that it was, finite if and only if algebraic. Right? See the difference? And more than that, where if the degree of, let's say, alpha j is equal to m sub j for j equals to 1, 2, dot k over the base field here f, then the degree of the extension k over f is what? It's less than or equal to what? Yes, the product of all the m1, m2, dot, mk. I mean, in some sense, it would just be equal if somehow these elements were sort of like independent in some sense, right? Like in our example here, the product, the degree of the extension, right, with my alpha 1 being root 2 and my alpha 2 being root 3, it was just 2 times 2, right? The degree of both root 2 and root 3 over q is 2, and the degree of the whole extension was 4. That's because the root 2 and the root 3 are in some sense independent, For an arbitrary set of generators, they wouldn't necessarily be independent, and because of that, you might get some kind of duplication in the things that they generate. All right, so it doesn't work out quite the same as my example. Corollary 18 says the following. It says alpha and beta algebraic over f implies, guess what? Alpha plus or minus beta and alpha beta and alpha over beta for beta not 0 are what? Also algebraic. And how do we argue that? Take your field, right? Extend by alpha beta. Look at f alpha beta. That's a field which contains alpha and beta, right? And it's finite, right? Because this is if and only if it's generated, so it would be generated by alpha and beta. That would be a finite extension, right? It's a finite number of generators, so it's a finite extension. And then inside the field f alpha beta, we can construct sums, differences, products, and quotients because it's a field. And all of those things are happening inside this finite extension, right? Therefore, finite means algebraic, which means that these are also algebraic. But if you think about the task of just doing it directly, right? Like this is actually theoretically very easy thing to argue, but look at what it means pragmatically. Like how do you actually build the minimal polynomial for these things? If you have the minimal polynomial for alpha, minimal polynomial for beta, what's the minimal polynomial for like alpha beta? I mean, it feels like it should factor the product of m alpha and m beta, right? But I don't know. We don't have to do any of that because we have the argument I just shared with you, which is nice. Now, this example will kind of blow your mind a little bit. So if we consider the complex numbers over the rationals, all right? And you can let q bar denote subfield of rational numbers which are algebraic. All right? These are the so-called algebraic numbers. How big is this subfield? Why is it a subfield? See, if you take two algebraic numbers, then it's closed under what? Products, differences, sums, differences, products, and quotients. That's all you need for the subfield test, right? Corollary 18 gives a subfield test for algebraic numbers, this Q bar. So the algebraic numbers form a subfield of the complex numbers. And he explains in the book why these are countable. So it's huge, but it's still only kind of as big in terms of cardinality as the rational numbers, or the natural numbers, if you like. And then he argues that you could, of course, also look at, if you look at his other examples, if you look at Q bar intersect the real numbers, that gives you a subfield of real numbers, which would be the constructible real algebraic numbers. And he argues that there are, in fact, infinitely many real numbers which are not of that form. Right? So if a countable number of them are algebraic in this sense, then in fact that means what's left is the continuum, right? There's infinitely many irrational numbers. Theorem 20, he has, if k is, theorem 20 says the algebraic extension of an algebraic extension is algebraic. All right, I'm not going to write it down. Yep.
Is there anything that wouldn't be included in the intersection?
Oh, this? Yeah, I mean, if you know, what's algebraic? I mean, I is algebraic because I squared is minus 1. So like x squared plus 1, you know, minimal polynomial of I over the rationals, I suppose. I mean, there's tons and tons of imaginary algebraic numbers. Those would not be in the reals. So that when we intersect Q bar with R, we just keep the real algebraic numbers. That's the. I hear what you're at. Yeah.
Did that answer your question completely? It did. Okay. So maybe I'm missing something.
Uh-oh.
But if Q bar is the subfield of the rational numbers.
Subfield of. No. That is the what's the word? The kryptonite, the logical kryptonite on the board at the moment. So that's making us all ill, like mentally ill. So we don't want that. Complex.
Okay.
Complex numbers. Yes. So if we look at complex numbers, the subfield of, I mean, in other words, there's a picture here. C, there's Q bar, and then below there's Q, right? And there's this tower of fields. Q bar is an intermediate between the rationals and the complexes. In contrast, over here are the reals, and in between we can look at Q bar intersect the reals over, of course, the rationals down here. Thank you. Oh, man. Well, I'm sorry, guys. I just sometimes don't see stupid things I've written. You know, I should see if I don't. Finally, Proposition 21. Proposition 21. So first of all, definition. If you have K1 over F and K2 over F extension fields, then K1, K2 is the composite of K1 and K2. I mean, it's It's a field which contains both K1 and K2, and it's the smallest such field. All right. Proposition 21 tells us how to deal with such a thing. Here's what Proposition 21 says. It says that the degree of K1, K2 over F is less than or equal to the degree of K1 over F times the degree of K2 over F. And the arguments supporting this are really just mired in chasing down like what a basis looks like for the extension of the extension and just like sorting through the details. It's not that complicated. I would encourage you to read this couple pages of Dumbit and Foote. It will take me a long time to get it on the board, and it won't really add anything when I do. But this is the theorem here, and there's a picture he has which is really quite nice. You've got K1, K2. We could put K1 over here. We could put K2 over there. F is down here. So let's see here. M2, M1, and I guess this is less than or equal to M1, and this one over here would be less than or equal to M2. That's what the theorem says, is that so this is M1, M2. But, fun fact, like K1 over F must divide K1, K2 over F. Why is that? To quote my little brother, as he used to say, once upon a time, "'Cause be why." But, I mean, why? Why is it true? And Andrew would say, "'Cause be why." Like, it's not a, Andrew, it's not a saying. He'd be like, "'Cause be why." He was 4 years old, though, in his defense, you know. And he was adorable. But some say he's still adorable. I don't know. Let's see here. Why is this? This is because K1 is a subfield, I mean it this time, of K1, K2. I mean, you can kind of see it in this picture. All right? Because K1, K2 is the smallest field which contains both K1 and K2. Right? So, what does that mean then if K1 and K2, if they have extension degree over the base field, which is relatively prime, what does that say about the degree of K1, K2? What's that? They're equal. So I'm saying if K1 over F and is, you know, relatively prime to K2 over F, then the degree of K1, K2 over F is what? Oh, you're saying it's equal there. I would agree. The formula becomes, inequality becomes equality. The thing we were looking at the start of today is such an example. See, because if you look at, see here, and I've forgotten my example, but he says, composite of the field Q adjoin root 2, if we take like K1 equal to Q adjoin root 2, and K2 equal to Q adjoin the cube root of 2, right? This is a degree 2 extension over the rationals. This is a degree 3 extension over the rationals. So what is K1, K2? K1, K2 is Q, which is formed by adjoining both root 2 and the third root of 2. And he says, oh, okay, well, that's really just Q adjoin the sixth root of 2, since what? Since 2 to the 1/3 over 2 to the 1/2 is 2 to the 1/6. Flip that around. So 1/2 minus 1/3 is 1/6, right? So the ratio of these is that, which means that this really is just Q adjoin the sixth root of 2. So the composite of these two fields is Q adjoin root 6 over 2. And this all works together because 2 times 3 is 6. And of course, we also know this is a degree 6 extension because, well, x squared minus 2, x to the 6th minus 2 is Eisenstein by, well, Eisenstein, yeah, equal 2. So we start to get a lot of tools to work with looking at different field extensions and so forth. I think it takes a while to really absorb all of this and like get good at it, but I hope we're starting to get there. The next section is on something really, really different. All right? And so the next section is on the classical straight edge and compass constructions, namely doubling the cube, trisecting the angle, and squaring the circle. And so I don't think it'll take me a whole class period to do it, but I'll do it next time. But just to give you a flash forward, all basically we do is explain that the numbers which are constructible all appear as degree 2 to some power extensions of the rational numbers. So if a number is constructible in terms of classical geometry, it means it's an extension over Q of degree 2 to the m for some m. All right? And then arguments are given which show you that doubling the cube or trisecting the angle are not amounting to a degree, an even power degree extension of the rational numbers. In fact, the cube is like a third order extension, and also trisecting the angle amounts to a degree 3 extension. Therefore, it's impossible to double the cube or trisect the angle. The proof, though, is mired in this stuff. But I won't actually do the geometry stuff in here. I'm just going to claim it and like wave my hands a lot. I leave the compass and straight edge stuff to. Oh, should I do that in here? Maybe, since you're not going to learn the other one. So are you the guys who are after Dr. Smith to do a special topics class in number theory?
Oh yeah, I talked to him about that.
Okay, so
Did he talk to you about it?
he's weighing the options.
Yeah,
You need to.
him at least.
Yeah, you need to like bribe him somehow, right? Make it worth his while.
Totally do it.